Okay, let's work through one of these example problems in Excel. Now, some of these will be just easier to do by hand, so that's perfectly fine to do them by hand. Here we have a structure. We want to find the internal forces, which is axial, shearing, and bending moment at point J down here for the structure indicated. Okay, so before we go to the internal forces, the first thing we need to do is to come down here, solve for the reaction at the supports, and then once we have that, we can also solve for the reaction here, and then we can go over to J. One thing to notice here, member BD is a two-force member. He is in tension, so he's pulling down. You could replace this guy with a rope if you want. That's how you know if it's in tension or not. If you could replace it with a rope and it would be stable, you know it is in tension. Okay, so we have this guy in tension, and if this member is pulling down, that means the reaction at D is going to be up, and we know this direction. Okay, so I'm just going to go ahead and find the angle here. So if I look at this green angle, I've got 10 versus 24, and just to turn that into degrees, so I'm going to say equals degrees. And this is going to be the arctangent of that 10 inches divided by that 24 inches. Okay, so there's our theta is 22.6 degrees. And to solve for this, let's go ahead and take the moment around point C. So the moment around point C, it's going to be 160 pounds times, let's see, 14 plus 8 plus 8. So that would be 30, I guess, 14 plus 16. That's going to be one moment, and then the other moment is going to go from C up to D. So let's see if we can figure this out. Okay, so taking the moment around C, I'm going to take this question mark to C, because C is where we have the most unknowns. We don't know the magnitude or the direction, so X and Y, so that's the best place to take the moment around. First thing, we're going to go from C to A to this 160 pound force. So we have negative 160, and we have 14 plus 8 plus 8. We're going in a negative direction. This combination from C to the 160, that is going to give us a positive moment, that 30 times 160. The next moment we're going to do is from point C to the force that's applied at D. Now we can break this into X and Y components to go from C to D and then get the X and Y components of D. Or we can come over here and just try and find the shortest perpendicular distance to the line of action of the force D. And this is the real advantage of that two-force member, is that we know the direction. So if we just make a little right triangle in here, and we know the hypotenuse of that triangle is going to be 16, so this little perpendicular distance, that's opposite that 22.62. So here's from C to the line of action of this force, to calculate this, is going to be equal to 16 times the sine, and we have to put that into radians, of that 22.62 degrees up here. I'm just going to click on that cell. Okay, so there's our position vector, and the force in this case then is going to be just equal to 30 times 160 divided by that perpendicular distance. So we end up with a force that is 780 acting right here at this point D. Okay, so here's that 780 force at D. Let's go ahead and break him into his X and Y components using that angle we calculated, 22.62 degrees. So over here, the X component is going to be equal to 780 times the cosine radians of that 22 degrees. And notice wherever I have something calculated, I'm not going to type in the number. I'm going to actually use the cell for that. So the opposite side is the y component, so that's going to be the sine radians of this 22.6 degrees. So there's the x and y components of the force at D. And the last little bit we have to solve for is what these external forces at C are. So here we go. The force at D is 300 up in the y direction and 720 to the right in the x direction. To balance those forces, we're just going to fill in our force table. So that means the force at C, we're going to have just equal and opposite forces right there. So this is going to be 720 to the right versus 720 to the left over here. And then to balance our y forces, CY is going to have to be equal to negative of these two added together. Okay, so there's our CX and CY, and then the total force at C, of course, is the combination of both of those. Okay, so that's kind of the chapter 6 part of it, is solving for all the reaction at the supports. And now that we have the reaction at the supports, the next step is to carve in and find out what is happening internally at point J. Okay, so here we are. We've solved for the reaction at C. We're going to isolate this little piece of the bar and just draw a free body diagram of this little chunk heading over to point J. We didn't have to solve for what's happening at B because we can grab this from either side, remember. So let's just grab it from this side. And you can see that the axial force, 720, is in the x direction. So our axial force will be 720. Our shear force will be 140. See how those are equal and opposite? The last thing to solve for is our moment. To solve for the moment, what we're going to do is take the moment around point J. Remember, whatever point you take it around, the forces don't go into that moment calculation. So this is just the internal resistance to bending that is being created by, it looks like just this 140 force in the y direction. So we're going from J to where the force is applied. So we're going over 8 inches. That's our position vector, is 8. And then our force is in the 140 direction. So in order to fight that moment, so it's team red versus team blue here. So 8 times 140, that's 1120, and this is the moment that is inside of that beam fighting back. So if you come back to this diagram again and think about how this beam is going to deform, okay, so that 160 at the end, it's going to be kind of pushing it down and wanting to bend it. And to fight against that, inside of it, it has to resist that bending moment. Or if you think of the 140 down over here, so there's a little equal and opposite pair of moments inside of the beam where it's getting chopped apart right there, that it wants to bend and it has to fight against being bent in here. So here is the final answer. We have a shear force of 140 fighting against that 140. We have an axial force of 720 fighting against one another. And we have an internal bending moment of 1120 pounds per inch if we sliced into the part right here at point J. Okay, hope that wasn't too confusing.